Thank you. Good afternoon. My name is Sarah Tessendorf. I've come here from Boulder, Colorado. I'm very excited to share some of the recent advances that we've been making in our group regarding the state of weather modification science, and especially make some remarks as it applies to the goals of this workshop and this moonshot program. Okay. So I have three key messages that I want to convey today. The first is that some recent studies that we've been doing have proven that cloud seeding works to enhance precipitation in winter orographic clouds. Okay. The second is that recent advances in computer modeling are enabling us now to conduct innovative research and improve our understanding of cloud and precipitation processes, and this includes our ability to study the impacts of cloud seeding. And third, there are numerous ongoing challenges in this field of weather modification, and one that relates a bit to the LC topic that we just heard about is how the public perceives it or even maybe has misperceptions about it. All right, so to introduce cloud seeding, we've heard about it a little bit in some of these prior presentations, but I'm going to give some background on it here. So the type of cloud seeding I'm going to talk about is a weather modification technology typically that aims to enhance precipitation, and we've been hearing about it in the opposite sense earlier today. But this is the main form of precipitation enhancement research that I've been working on. There are other aims that cloud seeding is used for as well. Some programs use it for hail mitigation or even to disperse fog. This is a map of the western United States showing where cloud seeding operations are being done right now at present. It's occurring across many of the western states. The western states are where we have mountains, and so those are primarily programs targeting the wintertime orographic precipitation. And then across the central parts of the U.S., shaded in green, are programs that are seeding summertime convection, either for precipitation enhancement or hail mitigation. Of course, this is also happening in many countries around the world as well. This image walks you through the conceptual model for the scientific process behind cloud seeding to enhance winter orographic precipitation. And the primary goal of this is to increase snowpack in the mountains, but oftentimes the programs using this type of cloud seeding really want additional water in the streams. And so it's not just for the snowpack enhancement, often that ultimate goal is for the snow to melt and enhance the water that we get into the streams. But the steps shown here, the first step is that we need a cloud, and that cloud needs to contain supercooled liquid water. So that's the form of water in a liquid state that's colder than the freezing temperature. And the reason why I emphasize this first step is because it basically is pointing out that we are not creating clouds when we talk about cloud seeding. We really need that cloud to be present with the supercooled liquid water. When a cloud has supercooled liquid water present, it's often a sign that it is not efficiently producing ice on its own, and so it's not producing as much precipitation as it could otherwise, so it makes it a good candidate for cloud seeding. Once we have these types of clouds, we will then release silver iodide is the seeding material often used here because silver iodide has been shown to be an effective ice nucleating particle. The types of ways that this is released is often from ground-based generators or from aircraft. This third step is also very important because not all of the time can we assume that the material gets into the cloud. Aircraft seeding has the opportunity to release the material right in the cloud, but especially from ground-based seeding, it's important that those particles disperse into the cloud. And then once they get into the cloud at temperatures where they can nucleate, they'll form ice. And then once the ice forms, that process of ice-based precipitation formation can take place. And what that will do is rapidly form snow at the expense of the supercooled liquid water in the cloud. So essentially, we are converting the extra liquid cloud water into additional snow. So we're not making anything up out of thin air. We are just squeezing out a little bit of extra precipitation out. I also just included a few photographs on here to show what a typical ground-based generator might look like. In the lower left, note that the one picture without snow shows that it's up on a pretty high tower. The one with snow is showing how the snowpack can accumulate up to the base of that tripod there. The other photograph is showing the backside of an airplane wing. The way that we seed with an aircraft is a specialized aircraft that has these racks on the back of the wings, and then you can put the pyrotechnic flares that will burn the silver-iodide material on the backs of those. So we heard a little bit about the initial origin of cloud seeding back from the 1940s. This is some additional context on that, because the reason why I wanted to bring this up is that this concept has been around for a long time. But we've only just recently proven the entire conceptual model from altering the cloud to enhancing precipitation on the ground. And I'll show you those results in a moment. But so back in the 1940s, a lot of excitement was there because we had this proof of concept initially by this photograph shown here that if we seed a cloud, it can alter the cloud. And in this case, the racetrack pattern that was flown by the aircraft was releasing dry ice, and that was converting that liquid cloud into an ice cloud and depleting the cloud. But it's taken over 70 years to prove this entire conceptual model that altering of the cloud led to precipitation on the ground for a number of reasons. There's a lot of natural variability in the ways that clouds form and produce precipitation. So it's been very hard to isolate the effects and detect the effects from cloud seeding. So it's that effect determination that was mentioned in an earlier presentation. And in these earlier decades after this was discovered, our ability to observe, our different observational technologies were not as advanced as they are today, as well as the computer models were not as advanced because computers in general were slower. So the various ways over the years that we used to try to study these impacts from cloud seeding were, one, by collecting physical observations. And for this type of cloud seeding, some very important observations to collect would be the measurements of the supercooled liquid water in the atmosphere, high-resolution precipitation data, either from snow gauges or radar, and temperature and wind data as well, such as from radiosonde data. One problem here is that we do not have routine networks to observe all of these different quantities. And even when we do deploy a few of these measurements, it's never as dense enough spatially for us to really get a good picture. The other thing about using just observations alone to study cloud seeding is it's not a controlled experiment. So it's that effect determination challenge where once you seed the cloud, how do you know what you're observing would not have happened naturally? So it was very challenging. So a lot of the studies turned to statistics. And statistical studies, in particular randomized statistical experiments, similar to pharmaceutical trials were done, where you randomly seed some of the clouds and don't seed the others, and try to see if you can detect the effect with statistics. To do this, you need very good quality and high-resolution precipitation data, though, because if that's the measurement you're trying to measure the effect in. But you also need years of data to get a large sample. Statistics need a sample size in order to be able to extract the effect, especially if the effect is relatively small compared to the natural variability. So over the years, it was very hard to get statistical significance in these. And it was determined that most of these studies would have needed way too many years of data than they were able to collect. So computer models is another approach, and that's the one that's really been used a lot by the current studies in this moonshot program, and currently is giving us a lot of promise. But in the lead up to the last 10 years or so, before we had the supercomputers of today, our computer models just weren't high enough resolution to really represent the clouds and precipitation. And there's large uncertainties in the models. We heard about that from our earlier keynote, and that uncertainty still exists actually, and that's why some of the research that Dr. Park is doing is so important. But if we fast forward to today, well, actually 7 years ago in 2017, we did a field experiment called SNOWY, which stands for the Seeded and Natural Orographic Wintertime Clouds, the Idaho Experiment. We love good acronyms for our field projects. We went into the field with radars that were on top of mountains where normally we don't get to see the clouds because the mountains are blocking other radar data from the routine networks. And we were doing cloud seeding with an aircraft. When the aircraft flies back and forth across a track that's perpendicular to the wind, it produces a dispersion pattern of the silver iodide that's like a zigzag. And the interesting thing about that is Mother Nature does not produce zigzag patterns in the clouds. So it was our modern day racetrack pattern in the sky experiment. We seeded these clouds multiple times in different storms, but in a handful of these storms, 3 of them specifically, we very clearly could see this pattern. The reason we could see it is because these clouds were not producing ice naturally. They were supercooled, but not cold enough to produce ice on their own. And so when we injected the silver iodide, it produced ice, and that ice is a very good reflective material for the radar. So you can see the zigzag pattern. This was a huge breakthrough to see this and observe this in the field program. With that data, we've been able to answer a lot of questions then about that whole conceptual model. We've seen that the radar data shows that there was ice forming, and then here we can trace it to the ground because we also had an aircraft that was flying with another radar on it. So these are vertical cross-sections of airborne radar data over time, and we were able to trace those lines as they passed over and as the aircraft flew through all the way to the ground. And in addition to that, we had high-resolution snow gauges on the ground as well, and so when we zoom in on the radar data that showed the zigzag pattern, we can see when it passes over our snow gauges. And in this case, we have this snow gauge here called Silver Creek, and when the reflectivity line passes over the gauge, which is the reflectivity is in gray, so that it's increasing, the blue line is showing the precipitation accumulation as measured by the snow gauge as well. So we were able to measure that precipitation increase on the ground. We were able to do this in multiple cases. As I mentioned, we had at least 3 cases where clear seeding lines were observed. And so we were able to zoom in on the radar data and look at our snow gauge data underneath each of the gauges, or underneath those radar patterns. And we measured anywhere from 0.05 to up to 0.28 millimeters of increased precipitation in the gauges as the seeding lines were passing over. The other thing we were able to do is we were able to estimate the snowfall from the radar reflectivity data itself. We refer to these as ZS relationships for radar reflectivity to snowfall. The thing is there are multiple different ZS relationships in the literature. It depends on snowflake density and a lot of other parameters. So there wasn't one that was going to work, but what we did is we compared the snow gauge data with the spread of different known ZS relationships to create kind of a mini ensemble spread of what the radar estimated snowfall would be. And in doing that and comparing it with the gauge data, so the gray shading here is the range from the ZS relationship, and then the dotted lines here in red, here in blue, and cyan, and here in blue were the actual snow gauge data. And you can see that timing sometimes was a bit off in this case, but the overall total accumulations and even some of the timing in the others were actually quite good. So we were able to then show that the spread of these ZS relationships does encompass the actual observations, and then using the best matched ZS relationship, we were able to map out spatially using the radar data where and how much additional snow fell in that zigzag pattern. And we were able to do this in each of those 3 cases. So this was also a major breakthrough because not only were we able to measure the impact at snow gauge sites, which is what statistical programs try to do. They have gauges and they're trying to measure at a specific site, but we were able to map out spatially where the effects were occurring using the observations in this limited set of cases that did not have natural precipitation occurring. I want to emphasize that because if there had been natural precipitation occurring, we would not be able to see the zigzag pattern. And the majority of cases, have some natural ice or snow forming. So we were very fortunate to do this in a few cases where that was not the, where we were able to readily detect it, but that's not always going to be the case. So we cannot rely on always seeing this radar signature, so there's got to be other ways to do that effect determination. So that's where our research really has to go next, is we now have proof of this entire conceptual model for winter orographic cloud seeding based on the data from the SNOWY project. But the questions that we need to better understand still are where and when does it work most effectively? It's not going to work equally in every storm. And then how do we confidently quantify the impacts of cloud seeding? As I mentioned, in the cases where we cannot see the effect on the radar, we still need ways to be able to identify the effect and quantify it. We also are interested in how does the cloud seeding impact the snowmelt-driven stream flow? And how cost-effective is it? That's another key question. We can't really answer how cost-effective it is unless we know how effective it is. So that some of those first questions really will inform the latter questions. But the good news is we're working to address these questions now with some of the new advances in computer modeling. So I'm going to walk you through some of the key breakthroughs that have taken place in computer modeling that have led to our ability to study this with computer models today compared to what we could not do in the earlier decades of cloud seeding research. The first major breakthrough came almost 15 years ago now, where we were able to show how orographic precipitation in the mountains can now be realistically represented by computer models. And one of the keys for doing this is running high enough resolution. Supercomputers of today allow this to happen. The key for this, as you can see here, so we did this study in the limited region of Colorado. It's the Colorado headwaters. This section here was run at 36-kilometer grid spacing, whereas this one was 2-kilometer grid spacing. And then this here is the SNOWTEL snow gauge data measurements. One of the reasons that when you compare this 36-kilometer to 2-kilometer is that clearly we're not even resolving the mountains themselves if we don't run high enough resolution. And the mountains themselves, oops, went forward. The mountains themselves are what are driving the clouds to form to begin with. And so they have a huge influence on the amount and location of precipitation. So if we compare a region here in the northern part, at 36-kilometer grid spacing, it says that the annual precipitation there would be around 350 millimeters, whereas the annual precipitation, when we look at the high-resolution simulation, is over 1,000 millimeters. So this is a huge difference by just running in higher resolution. But thanks to supercomputing advances, we now have run at high resolution for very long time periods over the entire continental US. And so we've been able to do a lot of great research studying these three-dimensional simulation outputs almost in exchange for what's missing in the observational record, because we're actually reproducing data and information in between where we don't even have snow gauges and so forth. So this has been a huge breakthrough that we can now get the clouds and precipitation right if we run high enough resolution. The next component was that we developed a parameterization to simulate the effects of cloud seeding. So this simulates the physics of the cloud seeding with silver iodide process. And Dr. Park presented one of the other graphics that walks through the different microphysical processes that are being represented here. This animation illustrates it visually so that you can see over these two mountain ranges, there's the white color is the supercooled cloud. And then the cyan color is where we insert in the model simulation silver iodide. It'll show up again here. In this simulation, we're inserting it at an altitude where an aircraft might fly, and it disperses downwind and interacts with this cloud, and within that, you'll see some yellow, maybe, right in here if your eyes are good. Oops. Too far. There we go. And then that's the yellow is the representation of the ice forming, and then the green color below it is the snow. You'll notice that there's green contours around the rest of the region because this is the WRF model, the Weather Research and Forecasting model, that's designed to forecast and simulate precipitation and snow without silver iodide seeding. But what we can do with this simulation is we can run the simulation like this with silver iodide seeding. We can run the exact same simulation without the silver iodide and look at the differences. I also want to acknowledge our colleagues Masataka Murakami and Akihiro Hashimoto, who were also great collaborators in the initial development of this parameterization. So a third development that we worked on at NCAR that was initially not at all related to our cloud seeding research. It was the goal was to develop a hydrological model that could spatially distribute the precipitate or the runoff into the streamflow network, and this is called WRF Hydro. So this model was developed and is being used in the U.S. for flood forecasting and things like that. But the benefit of this development is that it couples directly with the output from WRF, and so we can use even now output from WRF WeatherMod to drive that hydrologic model. So with all of these three advances together, being able to run at high enough resolution to represent the precipitation in complex terrain, to have that parameterization that simulates cloud seeding, and a model that takes the WRF output, spatially distributed WRF output, to drive a hydrological forecast, we can now simulate cloud seeding impacts on both the precipitation and the stream flow. And so this is an image here of the precipitation change over a winter season from WRF WeatherMod simulations, using that to drive the WRF Hydro to then simulate the simulated stream flow volume change. Of course, models, though, still have uncertainty, like I mentioned earlier. This is a great opportunity for us to have a controlled experiment where we run that seeding simulation minus the control experiment without any seeding, but there's uncertainty in that. And so there's a few things that we've been doing to address the uncertainty. One of those things is use the data that we've collected in SNOWY to compare with our model simulations. That was one of the real important goals of SNOWY, is because we had developed WRF WeatherMod, but we didn't have detailed data to compare with it. And so in this example here, we've got observations from the cloud radar in the bottom right showing you the couple seeding lines at that time. We've got an animation from the model now in the upper right. This magenta color here are those two seeding lines. That's the silver iodide in the model. And then the color is the precipitation condensate that's being developed from them. So you can see how that compares fairly well. We have an upper cloud layer and a lower cloud layer, very much like the observations in this case. And then on the left, we have time series where the aircraft, we had a research aircraft, was flying through these clouds, and in these two shaded time periods here, it flew through those seeded lines, and the red data are from the King Air. The blue line in here is the model with the seeding simulation showing us, for example, a depletion in liquid water content compared to the control simulation, which was very similar to what was observed, as well as an increase in the ice water content here in this panel in those two seeded lines. So basically, we observed and simulated the liquid water content being depleted and the ice water content being produced. In general, from these comparisons, we've been able to show that the model can replicate what was observed in SNOWY. Does it always get it right the first time? No. So there's still other sources of uncertainty that we need to account for. And one of the ways that we're accounting for that is by using ensemble modeling. So this graphic here just depicts that there's initial condition uncertainty, for example, that can lead to different results in the overall forecast or simulation. And if we just run one simulation, which is represented here by this red line, we call that a deterministic forecast. You don't know for sure exactly if it's going to represent the truth or not, but if you run an ensemble where you vary the initial conditions, for example, you'll end up with a spread of forecasts that generally represent the climatology and will have a better chance of representing your actual conditions that were observed. So we did this initially in a study in 2018 where there was a statistical experiment looking at the impacts of cloud seeding in Wyoming. And WRF Weather Mod had just been developed. We ran 10,000 simulations in order to try to recreate the results of that statistical experiment with an ensemble. So that experiment had 2 snow gauges that were the focal points. And so these spreads, these box and whiskers, are showing you the spread of the results from the model simulation ensemble at those gauge sites. And this one on the right is just showing a combination over both. And if we look at the interquartile range of this spread, it was 3 to 7%. The statistical experiment suggested a 3% increase. Although it was not statistically significant, we were able to reproduce within that spread results very similar to the statistical experiment. The other thing that we do with the ensemble is we can look at metrics like the ensemble mean, which is shown here, or we could look at max and min. We can look at any part of that spread, the distribution of that spread. In this case, this is the model's representation of the natural precipitation from the control simulations versus the simulated seeding effect change or enhancement on the precipitation. So there have been a lot of advances, but there are some ongoing challenges in this field. As I mentioned earlier, there are still remaining questions that we need to address related to the efficacy and the cost effectiveness of winter orographic cloud seeding. We need to confidently quantify the impacts of weather modification, not only in the winter orographic clouds, which we have growing confidence that the computer modeling capabilities are able to get us there, but there's other types of weather modification beyond winter orographic precipitation enhancement that the science is much less advanced on, including the summer convection precipitation impacts or hail mitigation. Convection in general at the small scales is much more challenging to simulate in the models. It's got a shorter time scale, smaller spatial scale, and much stronger dynamical updraft strengths, for example. And so those are definitely more challenging systems. And so that is exactly the challenges that the Moonshot program has before it, for sure. And then the other challenges that are ongoing are related to how we educate people and the public about cloud seeding and correct misperceptions about it. It's important that people understand how it works and what it does do versus what it does not do. Addressing their common concerns and overcoming some of the misinformation that's out there. There's a lot of things that get attributed to cloud seeding that in no way could be due to cloud seeding. And I feel like most all of these challenges will be very similar to those faced by the research in the Moonshot R&D program. So I want to walk through what some of the common concerns are in the world of cloud seeding, winter orographic clouds. I get asked these questions every time I give a presentation on cloud seeding. Every time. If one of you wanted to ask these questions, I've already got the answer. But no, this is the public meetings, science conferences, I always get asked these questions. So one concern is about the extra area effects. Does cloud seeding remove water from the sky that would have been precipitation elsewhere? And more candidly, people will say, are we robbing Peter to pay Paul? Another concern is about the potential environmental impacts. Does cloud seeding with silver iodide lead to dangerous levels of silver in our snow and water? And then there's concerns about the potential for cloud seeding to contribute to flooding and weather hazards. So will cloud seeding create floods? So let's talk through each of those. The first question about extra area effects. This one's a very challenging question to fully address because if it's been so challenging over the many decades of cloud seeding research to detect and attribute the effect of cloud seeding in the intended targeted area, the effect outside that area will likely be more diffuse and even harder to detect. So this is a very challenging question for sure. Conceptually, we've often referred to this pie chart, which is the overall amount of water vapor in the atmosphere. We call it our water vapor budget. As water vapor comes into an area and a cloud is formed, it does not all form the cloud. So some of that water vapor does not nucleate or condense into water. So in this pie chart, we say maybe half of that water vapor does. The rest of that water vapor continues blowing downstream wherever it's going to go. Then in a cloud, we know not all of the cloud fully precipitates out. A lot of precipitation efficiency studies have been done and show that precipitation efficiency is generally around 30%. It varies by storm. It's that lack of 100% precipitation efficiency that gives us the opportunity to cloud seed for extra precipitation to begin with. But so we're getting to a smaller part of this overall pie chart where we actually have precipitation. And then depending on how much we augment the precipitation, that will determine this yellow slice of the pie. It's generally conceptually thought to be a very small slice of the pie. Now, the other thing about this pie chart analogy here is that that assumes that things are stationary in space and time, that you only have that much. But the atmosphere is always moving, water vapor is coming in and out, so this pie chart is still a simplification. I do hope that in the very near future, our new modeling capabilities will give us some new opportunities to study this question with the actual models. But before we can do that, we have to feel very comfortable that any small changes outside the target area are due to the cloud seeding and not due to numerical instabilities in the model. And that's a point that we're still working on to gain that level of confidence to use it for this purpose. We would also have to run the experiments over a very large domain, and that gets very computationally expensive. But this is something that's on the horizon now so that we can better answer this question. But to our best understanding right now, conceptually, this effect would be quite small. Regarding the environmental impacts of cloud seeding, there have been programs that have measured the silver in the snow, water, and soil in order to detect the silver. Some of these programs were doing these measurements hoping that they would see elevated amounts of silver to say that snow was seeded. So some of these measurements were done hoping to use that as a way to confirm the effect. Unfortunately to them, that was not very easy to do. On the plus side for the environment, it's really hard to detect. So these amounts are very small. And part of the reason for that is there is already silver in the environment naturally. It's in mineral dust, it's in the Earth's crust. And so this is a log scale chart showing various measurements of silver concentration, not anything to do with seeding, just naturally occurring. And when we went into the field, in this case in Wyoming, to collect these measurements, first of all, you have to go in the white clean suits because we're detecting and trying to measure very small trace amounts. But the amounts that they detected were down on the parts per trillion level, very, very small trace amounts that were in the snow in this region. And then they went and did these measurements in the year prior to any seeding, as well as during the years with seeding. So in this chart here, the red, bright red bar is silver that they were measuring, and this first one is the year before any seeding was done. So this red dashed line is showing you that baseline amount of naturally occurring silver in the snow. And in the years that they were doing seeding, most of the time it was less than that. There was only one year where they had a measurement that was similar to or just greater than that prior value. So again, they were not able to detect enhanced levels of silver due to the seeding, which means they can't use it to detect seeding as having occurred, but you can be rest assured knowing that it's not at high enough levels to be of concern about. In addition, this again is a log chart, log scale. The World Health Organization, or WHO, as well as the US Environmental Protection Agency, or EPA, has indicated what levels of silver would be of concern, and it's multiple orders of magnitude below those levels of concern that we've been measuring in these experiments. I will say that I think that there's still room for more ongoing monitoring of this, especially as more and more programs might start to seed and more silver iodide might be getting put into the clouds. But right now, it's a very small effect, and it's very hard to detect. And then the last topic of contributing to hazards. So the programs in the United States that conduct operational cloud seeding use something called suspension criteria. They set these criteria before the program starts, and they basically use these to suspend seeding when hazardous conditions could be likely. And the different types of hazards include unusually heavy snowpack in the area, extreme avalanche danger, unusually severe storms, insufficient reservoir capacity for the runoff downstream. Anytime there's a weather warning from the Weather Service, they will not seed. This chart on the right illustrates a situation where the snowpack is building up to be higher than what they would want it to be. So this is 2 different snow gauge sites looking at the snow water equivalent over a typical water year. The thin blue line is showing the 30-year median, so the climatological average, so to speak. And the green thick line is showing the accumulation from that given winter. And this thin red line at the top is essentially the cap, where they've said, if it gets above this point, which is this much farther above the median, we don't want to contribute any more to it from seeding, and so they will suspend. So at this is an example of one where it was not being suspended, and here's an example where by March it was above that line, and so they would suspend seeding to not contribute any more to what was already an exceptionally large snowpack. I do want to point out about this unusually severe storm suspension criteria. This approach is not going to work if the weather modification purpose is to target severe and strong storms. So there are some differences here to how we're able to apply this safety net or the safeguard for society that will be a big challenge for the Moonshot program goals. So just to summarize, these are the 3 common concerns, and we have found the impacts at this point to be rather small and not of concern, and or they're mitigated by these suspension criteria. But like I mentioned earlier, I think it's important for ongoing monitoring of these various things, as well as for improved methods of study to be utilized to better address these concerns going forward. Regarding education, this is the first of its kind online training module for cloud seeding. We have a training program called Comet that produces a lot of freely available online training modules on a variety of different topics. We've now developed one on how cloud seeding works, focused on winter orographic cloud seeding. It includes a lot of the content that I've presented today. It's a 45-minute module if you're interested in learning more. We need to build more of these because we need to have reputable, good, honest, and trustworthy resources to educate the public and stakeholders of all kinds on these different intervention methods. So we've started working on this, but we need to continue in this area. So regarding all of those 3 ongoing challenges that I mentioned earlier, I feel like there are certain needs that we have to continue addressing them. First and foremost, to address those remaining questions and confidently quantify the impacts, we need to continue innovative research with improved methods and new technologies. And that's one of the things that makes me very excited to be here at this workshop. It's very nice for me to hear the exciting research and really innovative modeling that's being done by this group. We also need research teams that involve physical scientists from a variety of disciplines and involve stakeholders so that we can adequately address questions that go beyond just atmospheric science. For example, in my team, we have hydrologists involved now as well, and we have a variety of different stakeholders that we work with. And then third, we need to make sure that we include a focus on education and engagement with the public. I think the LC work that's being done in this program is excellent. In our programs, this does not get involved at that high of a level. We do a lot of public meetings and education, but there's definitely room for more because the public definitely has a lot of questions, they have a lot of concerns, and they are sharing information that is not always accurate, and that's not going to help these types of programs if that continues. So I will just summarize with my 3 key messages again with these different advances in the science, from the snowy data that prove that conceptual model to the fact that our modeling capabilities have advanced, and that's really allowing for some really innovative ways to address these questions that we've had for many decades regarding cloud seeding. And we need to address the ongoing challenges in weather modification, which does include things beyond the physical science like the public perception and the LC-related topics. Thank you very much. I'll take questions.